Hello, Algebra 2 CP students. Hopefully your day is going well so far. Today, I would like to continue our discussion on solving quadratic equations by completing the square. By first asking you to try this do now problem on your own. It's a standard completing the square problem. You should get integer solutions, so no craziness happening yet. We will see a couple twists and turns today. But see if you can handle this problem on your own. Take about maybe 5 minutes, pause the video, try to do it yourself, and come back when you're ready. All right, by now, hopefully you paused the video, tried this problem on your own, and are ready to go by going over it. If you refer to the steps back in your notes, then that's good. Those steps are exactly what you want to refer to when you're doing completing the square problems. Eventually, and hopefully, the goal is that you'll get to the point where you no longer need the steps in order to do completing the square. But for now, if you need those steps, that's totally fine. Okay? Following those steps, the first thing that I would do to complete this square on this guy is I would isolate the constant term. I would do that first by subtracting the 96 over to the other side. That's going to give us 2x squared minus 40x is equal to negative 6 minus 96 is going to be negative 102. We can then divide both sides by the leading coefficient, step 2. So divide everything by 2, divide by 2, divide by 2, we would get x squared minus 20x equals negative 102 divided by 2, negative 51. So hopefully following so far, hopefully we're A-okay. Going forward from here is when we do a little bit of math off to the side. And if you remember from yesterday, we do this math off to the side in order to make this number show up that's going to result in factoring down to a matching pair. Okay, so how do I do that? Well, what I do is I take this negative 20, I divide it by 2, and I get negative 10. I then take that negative 10 and square it to get positive 100. Because negative 10 times negative 10 would be 100. We would then add that number to both sides. That gives us x squared minus 20x plus 100 is equal to negative 51 plus 100. From there, we're now able to factor, right, on the left and combine like terms on the right. On the right side, negative 51 plus 100 is 49, which you might think to yourself, ooh, it's a nice square number. That's pretty good, nice perfect square. On this side here, I can break this down, factor this down. We need x and x to make x squared. We're multiplying to a positive number, but the middle is negative, meaning we need two minus signs. And I would have 10 and 10 to get 100 when multiplied, and negative 20x when we do the inner multiplications here, the outer and inner, right? Negative 10x and another negative 10x would equal negative 20x. Now that we have this matching pair of factors, we can stick them together. And we say that we have x minus 10 times itself, which we can rewrite as x minus 10 squared is equal to 49. That's nice because now what we pretty much did is we condensed all this stuff down to just one binomial squared, and we can take the square root of both sides now in order to cancel out the squared term. So we get rid of that squared operation by square rooting both sides. That gives us that x minus 10 is equal to not just 7, remember. It's very important that we include that this is plus or minus 7. A lot of students always forget to include plus or minus. We need to do that to account for both the positive and the negative possibility. Because remember, x minus 10 could equal positive 7, because positive 7 squared would be 49. Or x minus 10 could equal negative 7, because negative 7 squared is also positive 49. It's like doing absolute value from Algebra 1, if you brought that up before. Okay? So, at this point, we can do pretty much exactly what I just said and say to ourselves, well, if I can find a value of x such that x minus 10 is equal to 7, that's good. Or if I can find a value for x such that x minus 10 is equal to negative 7, well, that's okay too. And just solving these little equations for x, we would get that our first solution would be x equals 17. Our second solution would be that x is equal to 3. And there you are. Problem solved by completing the square. Okay? Of questions? Hopefully that made sense. Let it sink in for a little bit. All right. Now, that's what we've seen when we've done completing the square problems with integers. We did a couple in class the other day. Here's another one for you now. What can happen, though, and what completing the square is particularly useful for, are problems that cannot be factored with integers and problems that have either radical solutions or, believe it or not, i's. Oh yeah, we're going to see that show up today. Okay, so consider a problem like this. You might be like, well, what the heck do I do if we end up with a radical? Sometimes the radical problems are actually not so bad, and almost in some ways, I don't want to say easier, but almost in some ways fewer steps than problems that don't have radicals. For example, something like this. X squared minus 10x minus 19 is equal to 3. Again, no matter what problem I throw at you, all you have to do is just follow those completing the square steps. So I would say the first thing to do here is isolate the constant term, giving us x squared minus 10x. Let's add 19 to both sides, is equal to 22. My next step would be to divide everything by the leading coefficient. Technically, the leading coefficient, the number in front of x squared, is 1. So you would divide everything by 1. Of course, dividing everything by 1 is not going to change the value of anything, but I'll write it here just for the sake of consistency, giving us now x squared minus 10x is equal to 22. From here, again, we want to find the number that we could write here such that we have those matching binomial factor pairs show up. In order to do that, I take this coefficient of x off to the side, and I divide it by 2 to get negative 5. I then take that value of negative 5 and square it to get positive 25. That positive 25 is important because now we're going to add that positive 25 to both sides, and that will ensure that my left-hand side comes out to be something that can be factored down into a matching pair so that they can be squished together into a squared term. That's why it's called completing the square, because we want that to occur every time. We want that to occur all the time. Going forward from here, let's see. I would break this down on this side to be, I believe, x and x. We need two negatives, and I think it's going to be x minus 5 and x minus 5. Again, when completing the square, we should always end up with those matching pairs. Over here, I get 22 plus 25 is 47. And you might be thinking to yourself, kind of almost thinking ahead, 47 is not a perfect square, so what do we do? Well, the answer is, first I'm going to condense this down to a squared binomial. X minus 5 times itself can be rewritten as x minus 5 squared. The answer is, we just kind of leave it alone. And I would say, if we take the square root of both sides, the square root and square cancel out here, that x minus 5 is equal to, well, plus or minus the square root of 47. I don't want to write it as a decimal. We've worked with radicals a whole bunch in first quarter. We can just leave that alone as the square root of 47. Now, if it could be simplified, which will be the case in a future problem that we do today, then you certainly would break it down just like we did in the first quarter. 47 can't, though. 47 is a prime number, so it cannot be simplified. Doesn't have a perfect square factor, so we just leave it alone. And at this point, we can split into our two solutions to say, well, when is x minus 5 equal to positive the square root of 47? And when is x minus 5 equal to negative the square root of 47? Well, getting x alone, I would just add 5 to both sides and say that x is equal to 5 plus the square root of 47. That's it. No need to write it as a decimal. In fact, do not approximate it to a decimal. Just leave it in radical form. Know that that's some decimal value. And over here, I would add 5 to both sides as well. And I would get that x could also be 5 minus the square root of 47. Again, that would be some decimal value. All right? And that's all we need to do. Hopefully that made sense. If you've noticed, even though we ended up with somewhat of an ugly radical at the end there, the process is still the same. And if you can't take the square root of whatever you end up with, well, then so be it. You just don't have a square root. You just leave it alone. Right? It's not a perfect square. You don't have an integer solution for that square root. Hopefully that made sense. Okay, let's do another one. We'll do a couple more just so you can get used to seeing problems that may not have integer solutions like that. Okay, consider something like this. What if I had 4x squared minus 16x plus 45 is equal to negative 7? I asked you to solve by completing the square. Stick to our process, right? First things first, let's isolate the constant term, subtract 45 over to the other side. That gives us 4x squared minus 16x is equal to, let's see, negative 7 minus 45, that's negative 52 if my mental math is correct. We can now divide everything by that leading coefficient of 4. That gives us x squared minus 4x is equal to negative 52 divided by 4, negative 13. Okay. One thing that you may be wondering is something that I just thought of as I was writing that step. Is it possible, you may be wondering, to get numbers here that don't divide evenly? Is it possible to get fractions? Same thing here. What's to stop me from getting an odd number before I take that number and divide it by 2? Would it result in a fraction? The answer to that is yes. In the wide world of mathematics, it is certainly possible to get values that would result in fractions over here. However, for our purposes in Algebra 2 CP, rest assured that any of these numbers up to this point will be integers. I'm not going to give you something like 52 over 5 and you'd have to leave that as a fraction of 52 over 5 and carry that through the problem. That's really out of the scope of Algebra 2 CP. It's unnecessarily difficult for not a great reason. Algebra 2 honors, maybe a problem like that is certainly fair game. But for our purposes in Algebra 2 CP, you wouldn't have to worry about that showing up. Okay, so just rest assured. In any case, I'll now go forward and off to the side, take my negative 4 and divide it by 2 to get negative 2. I'll then take that negative 2 and square it to get a positive 4. That positive 4, once again, is important because I'm going to add it to both sides, giving me x squared minus 4x plus my 4 now is equal to negative 13 plus the 4. Going forward from there, we can factor this left side and then just add on the right here. Negative 13 plus 4 is negative 9. Let's see, how can I break this down? We need x times x to make x squared. We have a positive at the end here, but a negative in the middle, so we need two minuses. We've seen that in all our problems so far, coincidentally. And here, let's see, I think we just need 2 and 2. Because negative 2 times negative 2 would be positive 4, and negative 2x, another negative 2x, makes negative 4x. Now that I have x minus 2 times itself, we can go ahead and write that matching factor pair, that double root, to use the proper terminology, as x minus 2 squared is equal to negative 9. You may already see some weirdness about to surface, right? Because at this point, you may notice, well, I'm going to take the square root of both sides, and on the right side, that would result in taking the square root of a negative. Oh boy, how do we do the square root of negative 9? Well, what's the square root of positive 9? The square root of positive 9 is 3. So the square root of negative 9, oh yeah, you guessed it, we need an I, right? Technically, it would break down to say the square root of negative 9. We can pop out that I. It's the square root of negative 1 times the square root of 9. The square root of negative 1 is I. The square root of 9 is 3. I would write this as 3I. Correct? So we can say that x minus 2 is equal to 3I. Don't forget the plus or minus. You almost forgot, didn't you? You almost forgot. I almost forgot. We almost forgot that plus or minus. Do not forget the plus or minus. Right? And yes, i's showed up. I told you they'd come back. They never go away once you learn them. So it's important that you know them. Negative square root means you need an I. Now, we can just break off into our two problems to say, well, x minus 2 should equal 3i, or x minus 2 should equal negative 3i. Once again, we'll just get x alone by adding 2 over to this side. Same thing over here. And we get our two solutions of x equals 2 plus 3i and x equals 2 minus 3i. Notice, just like when we did with complex numbers, I'm writing my answer in those a plus bi form. I know it's taking you back, but it's important that we keep that consistent. Okay? One last note about this that I want to make is notice that we don't combine these like terms. I don't do 3i plus 2 is 5i, right? This does not have an I in it. This does. They're unlike terms. You just leave them separated. That's a common mistake I see a lot too, is something like this. I would say negative 3i plus 2, and people would say, oh, that's negative 1i. Ugh, very bad. Not like terms. Leave them separated. Hopefully that was good. Hopefully that made sense. Let's do one more problem together, and then we'll be able to call it a day. All right, this one's going to have both i's and radicals showing up. Take a look. Let's do x squared plus 6x plus 88 is equal to negative 9. It may be getting a little stale to keep repeating those first couple steps, but it's important that we keep that mindset of isolating the constant term. Subtract 88 to both sides here. Gives us x squared plus 6x is equal to negative 9 minus 88. Let's see, that's going to be negative 97, I believe. Right? I think so. Going forward from here, I would then divide everything by the leading coefficient. Well, if you notice, that leading coefficient is just 1. So yes, dividing everything by 1 does not change anything. But I always write it just to show that consistent step 2. Divide everything by that leading coefficient. Now that I've done that, off to the side, I can take this coefficient of x and divide it by 2 to get 3. I would then square that 3 that I just got to get 9. And that 9 is going to get added to both sides of the equation. That's the number that will ensure that we end up with a matching pair of factors. All right, hopefully you're hanging in there so far. Now I can go ahead and factor the left, combine like terms on the right. This gives us x and x to get x squared. Everything's positive, so let's keep everything positive, and 9 can break down to 3 and 3. Over here, negative 97 plus 9 is negative 90. Make sense? Okay, hanging in there? Hopefully. Going forward from here, how would I now solve this problem? Well, I would say, well, x plus 3 squared, x plus 3 times x plus 3, we can rewrite as x plus 3 squared is equal to the square root of negative 90. Everybody sees that, hopefully. Now, oh, I think I said the square root of negative 90 because I was getting a little ahead of myself. X plus 3 squared would equal negative 90. So now we would take the square root of both sides. The square root and squared on this side would cancel out, leaving us with just x plus 3 on the left. On the right, however, the square root of negative 90, you better believe that we can break that down. The square root of negative 90, first of all, I can pop out an I to say that's I times the square root of 90, right? Really, the square root of negative 1 times the square root of 90, which is I times, what's the largest perfect square factor that goes into 90? Oh yeah, it's all coming back, right? The biggest perfect square factor is 9, because we can say that 90 is 9 times 10. If you don't remember, or maybe you don't know off the top of your head what the biggest perfect square factor is, remember that you could always use your handy-dandy calculator and divide down the list of perfect squares. That list of perfect squares, maybe we could start at 64. Does that go in evenly? Nope. Let's go down to the next perfect square. 90 divided by 49. Doesn't work. 90 divided by 36. Doesn't quite work. It's a nice decimal, but it doesn't work. 90 divided by 25. Still doesn't work. 90 divided by 16. Rats. 90 divided by 9. And bam, we hit an integer. So if worse comes to worse, you could always use a calculator to traverse the list of perfect squares and find the biggest one. Wrapping this up over here, we would say the square root of 9 is 3. So I get I times 3 times the square root of 10, or in other words, 3i rad 10. So I'm going to replace this right over here, this broken down version of the square root of negative 90 with plus or minus, don't forget it, not going to forget it this time, 3i rad 10. Hopefully that made sense. A question that I always get every year is, do I have to break down the square root of negative 90? What if I just write I times the square root of 90? Do I get full credit? Do I get partial credit? In this, some instances I'm fairly lenient, but in this particular instance, since we spent an entire unit talking about simplifying radicals and negative square roots and breaking stuff down, you are definitely expected to be able to write this as 3i rad 10. And if you don't, then yes, it would be considered not completely correct. Definitely get partial credit. You wouldn't get the whole thing completely wrong, but definitely not completely right either. Now, going forward from here, there's only a couple things left to do. I can say, well, x plus 3 should be equal to plus or minus this value. So that means that x plus 3 could equal positive 3i rad 10, or x plus 3 could equal negative 3i rad 10. In order to solve for x, we just need to get it alone by subtracting 3 from both sides. Same thing over here. Again, these are completely different terms. We're not going to combine them. We are going to write it in my a plus bi form, making sure the real part is first, the I part is second. I would say that x is equal to negative 3 plus 3i rad 10. And over here, x is equal to negative 3 minus 3i rad 10. And those would be our two solutions. Notice that this is why we need something like completing the square, because with just factoring alone, we wouldn't be able to solve problems like that. We would not be able to arrive at those solutions just by resorting to factoring. All right? Hopefully that made sense. On Thursday and Friday, we are going to be practicing completing the square. I have plenty of practice problems prepared for you, along with an answer key to help you out. So hopefully you're able to use that to make some headway on completing the square problems. I would especially emphasize, once you get a handle on the integer ones, trying the radical ones and the ones with i's, because, not surprisingly, those are going to be ones that show up on assessments as well. Okay? I want to say thank you for your attention and focus today. I do hope you have a fantastic rest of your day, and I'll see you soon. Take care, everyone.